Well, welcome back. Have you noticed something this winter that perhaps has never been something you've seen before? What is that thing? The thing is, more people are getting sick this winter than really ever before. And you go, wait a minute, we've just been through the pandemic and that was a pretty bad time for a lot of people. That's a lot of people. Well, a lot of people are getting sick. I didn't say they're dying. And more people are getting sick this winter than really ever before. And why is that? I'm going to explain it to you because it is something special. It comes down to, here's the punchline, there's more different respiratory viruses rising at the same time. They're not all peaking at the same time, but they're all rising at the same time. So consequently, you have people that don't just have a flu or RSV or a coronavirus, they might have all three. And so this mix of all these viral respiratory problems are coming together. And so that has never been documented before. In fact, that is a trifecta of respiratory viruses that I want to tell you about, that you should know about. And this might be the new norm going forward. So this is that never happened before in terms of recorded viral respiratory history. Okay? So let's get into it. The data, what's happening, who's most at risk, who's most vulnerable, and what to do about it. I do think that there is a solution here that because of the COVID, we now have more information about respiratory viruses to the public in general that I've talked about before, the tsunami of respiratory viral data from around the world. I'm in the United States, but some of the best research from the pandemic is clearly outside the United States, whether it's Asia or South America or China and so on. You put all these together and you say, what is the consensus there? And it is amazing. So this is where we're going. Let's get into it. So why is everyone getting sick this winter? Respiratory viruses, flu, COVID, RSV. That's a picture of the 1918 pandemic about a lot of people being sick at the same time with an influenza outbreak. That's one of the three that we're going to talk about. Why this flu season is different than previous years and how to survive it unscathed. What you need for your viral respiratory first aid kit. Pretty clever, huh? Okay, a hint, it's all three respiratory viruses at once, the flu, RSV, and COVID. And they're different variants. What you learn in this video is why this flu season is different and what that means to you specifically, who is most at risk for severe symptoms and why, how to protect yourself, and when to do so. You ready to go? All right, first, don't take my word for it. I'm just a person looking at data, taking care of myself and taking care of the people that I work with. Here's what the CDC has to say about it. It's a little clip from them. Symptoms of the new COVID variant JN.1. Let me set the stage before you listen to that clip so you get the fuller context. So the combined effect of all three viral infections from the CDC, just end of December and January, is this. What we're seeing is three different color lines for three different viruses. You have COVID, influenza, RSV. What we see is like, well, they're not all rising and falling at the same time. No, they're not. Some are much more, and notice the black line is really the sum total of all three. So the sum total, the black line is really rising. But if you look at, well, why is it rising? Which is the one that's driving it up? It's all three pieces together. That's the part that has never really happened before. That trifecta, that three different viral families coming together and all their variants we're going to look at. I'm not going to spend too much time on the data, just enough so you get the big picture and know that it's actually happening. And it is true. So this has never happened before. As of the end of 2023 is what this goes for. So updated every Wednesday approximately at 12 p.m. The emergency department visits for respiratory viruses in the U.S. Isn't that amazing? In the U.S. So what you see here is, all right, there's the three lines, the three different colors, and you go, all right, it rises, it's at rose, and what was the blue one, the COVID-like, rose more in September when it fell down, now it's rising again, and the beige one, the RSV, it rose, and it's falling, and it's rising again. So if you look at each individual one, it doesn't look like a big deal. But the fact is, it's ongoing, or one resolves from one, they're exposed to another, and it goes on and on and on, sort of like a dishwasher. You know, you're getting spun around and spun around, reinfected by a slightly different variant of a different family. So it's a coronavirus family. So we call that COVID, right? That's short for coronavirus. And the coronavirus generally were considered the cold. You know, I have a cold versus a flu, influenza. Right now they cross over and they're put in the collective category of viral respiratory viruses. So what we're talking about is the flu. influenza A and subtypes, influenza B and subtypes, 3 different viruses all at the same time. So it's a viral respiratory trifecta, as I mentioned, composed of 3 viruses, not just one: RSV and variants, COVID and variants, flu and variants, again and again and again. They're all a little bit different, and you think that, well, you get set up against one, you should be good against the other. That's partly true. That's not true, but it's also something very different. Total respiratory illnesses is the purple, kind of what I just showed you. And I really blew up the last little piece here into December and January. So you can see the total emergency department visits. I used to call that ER, but now it's emergency department visits for respiratory viruses has really scaled up. So the total ED, emergency department visits for respiratory viruses, is far greater than the total of the 3 viruses. That is the difference. And this is what I feel is probably going to be the new normal. All 3 of these are going to be circulating around each winter, if you will, from pretty much October to April in the Northern Hemisphere. And you'll be exposed. And as it moves from east, which is where we think they come from, China, and they move west, the variants change. They adapt.
Everyone we know is sick. Andrea, what's going on with that?
Well, it certainly does feel that way. And if you're not sick, chances are that you know somebody who is. There's no doubt that we are seeing a lot of respiratory viruses swirling right now as we continue to see cases of RSV, COVID, and flu across the country. According to the CDC, those respiratory illnesses are now elevated in 38 states. Of those, 21 are experiencing very high activity. So that helps explain why it feels like almost everyone is getting sick right now. Flu seems to be increasing most dramatically, and CDC says it expects that those numbers are going to be continue to be elevated for several more weeks.
So the question to ask is, how is this year different from all the others?
In the past, we would have one disease that we were tracking or monitoring at a time, but have multiple diseases at once. It's not that they just have RSV, but they're getting RSV and COVID, or influenza and RSV, because all of these viruses are prevalent in our community.
Okay, we're going to break down a little detail. Not going to get too technical, but you're going to get the big picture, because I want you to believe this is actually true and it actually is happening. And it probably will happen again. And so you'll have a working vocabulary going forward, not only of what they're talking about, but of what to do about it. And are you on the list of people who are more vulnerable, more at risk? And it's not just the young and the old, but that's also part of it. All right, so RSV, respiratory syncytial virus. It's been around forever, as long as I've ever been in medicine, and certainly before I was ever born. I'm sure they probably goes back 100,000 years like all the other viruses. So, but this is what we're facing today. RSV can cause serious illness or death in vulnerable individuals, of course. Individuals that primarily are premature or very young infants, so children, with chronic lung diseases and congenital heart disease, and people who are over the age of 65. C'est moi! But there's a lot of other people. So they're very young and they're very old, and you'll have references at the bottom. So the coronavirus and variants. So COVID now. So we hear of COVID. Oh my gosh, COVID. Well, COVID is short for coronavirus, and coronaviruses have been around forever. So COVID-19 was the coronavirus of 2019, and that was the pandemic, and I'm not going to go down that rabbit hole, but that's where COVID-19 comes from, otherwise known as SARS-CoV-2 for that particular one. People of any age can catch COVID-19. They still track COVID-19, but it most commonly affects middle-aged and older adults. So that's 2 for older, 1 for younger, or 1 for middle age. And the risk of developing dangerous symptoms increases with age. COVID-19, who's at higher risk of serious symptoms? We're going to go into more details in coming slides. So here we go. We have COVID-19 wastewater monitoring. This is kind of the key in the United States. I don't know if they do this worldwide. I'm guessing they probably do. But it's measuring wastewater. So it's not just ER visits. That's what we did before, ED visits. It's wastewater measurements. So this is from COVID current wastewater viral activity level map from the CDC. Here's the map. And according to this, at the time, Tennessee was the rock star in a very negative way in terms of having the highest incidence relative to wastewater monitoring of COVID-19. And that changes. Let's get into it. So from the New York Times, we were in a big COVID wave, but just how big? Wastewater data has become perhaps the best metric to track the spread of the virus in the US, but it's an imperfect tool, of course. The curves in some of the COVID graphs are looking quite steep again. Reported levels of the virus in the US wastewater are higher than they have been since the Omicron wave, which was a couple of years ago, et cetera, et cetera. You can find that article. I'm not going to read it to you. But again, the wastewater monitoring serves, so why is that special? Why are they doing that now? It serves as an early warning indicator, which is pretty clever. So people with COVID-19 shed their viral particles in their stool. The particles are no longer infectious, but can still be measured in wastewater. Wonder who thought of that. Research suggests that the virus that causes COVID-19 can appear in wastewater 4 to 6 days before the first cases are identified, and serve as an early warning indicator before changes of other metrics. Levels of influenza and RSV can also be detected in wastewater. So there you go. So if you find somebody snooping around your water, your wastewater treatment in your neighborhood or your town, now you know who they are. They're from the CDC. Again, how big is this? So we are seeing rates going up across the country. This program now categorizes every state with available data at high or very high viral activities of the combined respiratory viruses. So SARS-CoV-2 wastewater viral activity levels are indication of what's to come, right? So now they're getting a little warning, call it about a week ahead of time, of like, oh, wait a minute, a week ahead of time, we're expecting an outbreak. So it's a little bit, okay? So here's what they did then. And this shows the very high areas are in, what do we have? Utah, Wisconsin, Vermont, Massachusetts, Florida, Georgia. That looks like Missouri, Illinois, and so on and so forth. But you get to see first Omicron, that was a year ago, and then things are quiet, and now it's picking up as of December of this particular data. So COVID-19 new hospital admissions, and COVID-19, another way of measuring it, percent positivity by week. So what we're showing is weekly positive testing. Probably not at, this could be a combination at home and in the hospital. More than likely it's at the hospital. And so you can see it was a pretty tight fit, but then actual hospital administrations exceeded the number of tests. So there's not a real tight correlation. Sometimes there is, sometimes there not, but there is. You can sort of catch the pattern, and you say, yeah, I sort of see it going together. These are all the flu subtypes, and I'm not going to go into all the subtypes, but I want you to understand when people say they got the flu, it's like, well, what variant? Most people have no idea what variant. Unless you go in to the ED and they test you for it, you're not going to know what variant you're having. You got the flu or you don't have the flu. And actually, you're not even going to know if you have the flu versus a coronavirus, COVID-19, or other, or the new variant, or RSV, or the new variant. So you have a respiratory viral infection that you want to have it taken care of because you feel terrible. So influenza positive tests reported to the CDC from 23 to 24. This is the subtyping I just showed you, but look at all the variants. So you'd have to go, all right, so what is the most dominant variant? The most dominant variant is the orange one. That's the N1, that's the H1N1, and that's been around for a decade and a half. So it's been around for a long time. It's not a new variant. And so you say, okay, that's still the dominant one. What's the yellow one? The yellow one is another subtyping not performed according to this. So the point is there's many variants. We're not all locked in the same one. The question then comes, when you get the flu shot, what variant is the flu shot against? If it's the dominant one, well, that means we'll assume it works or doesn't work. I'm going to step away from the whole virus or vaccine issue, but let's pretend for a second it does work. They still can only name one variant against which they'll give the flu shot. So it's got a problem either way. World Health Organization. And by the way, I'm not endorsing the CDC and I'm not endorsing the World Health Organization. I'm using their data. One thing I'll say very badly against the CDC, I think they are a complete shill for the big pharma, they've never seen a vaccine they didn't like. Hey, give me more vaccines. Give me more vaccines. And that's a whole nother issue, but I'm saying that they are blind on that aspect of information, but I'm using them to extract their data, not their propaganda. I think they've slipped in their quality of reporting, but their data is pretty dependable. Influenza laboratory surveillance information. Let's look at greater detail right here. The point here is, this goes back to 2005, year after year after year after year, there is a flu season. Some are almost non-existent. Others are huge and a big issue. So you can say, so here we are coming in through the end of the pandemic, even though that was coronavirus, and this is the flu, it was still a contribution, it was still present. And then there was a lull, and now it comes back, and then there's a big spike. So they don't call it the flu season for nothing. It comes each year, is the point. The pattern repeats each year. Big or small, it's a combination of different variants. Now we're just looking at flu tracking, right? Influenza, is it A or B? Most likely it's A. But these are all the variants, a combination of both. And it continues this year. So the flu, weekly hospitalization due to only the flu. Here we go. Here's the flu chart, basically arcing up here. And here's how it's been over past years. And here's April. Some of them are still just hitting their peaks of previous years. I could read out the years to you from 2014 to 2024, the last decade. We are really in the middle of this. So when I say it's a viral respiratory trifecta, I am not kidding. There's 3 different families of viruses coming at you, and you probably know somebody at the gym or at the school or wherever you go to work or whatever it is you do in your life that's sick, staying home, especially the older they are. Weekly deaths due to influenza year over year. So you can see there's the December 2019 from the flu, not from COVID-19. And now 3 years later, which was a year ago December, and now it's arcing up for this winter as well. So it's happening now. COVID admissions, flu admissions put together. So you can see here's COVID throughout the year. And then you see the flu from last year's flu season drop down to nothing. It's amping up as we get into we're now into February now. Okay, so my point is every year respiratory viruses increase in the winter. Pretty straightforward. However, having all 3 viruses rising together has never happened in terms of viral respiratory recorded history. So you can say, well, maybe it always has happened and we just never recorded it. You could argue that, but it'd be, not something we could dismiss really. Is it a major calamity? Do I see it as a major calamity? No. It just means that most of us will get sick if we haven't yet been, or more than likely we know somebody who is currently sick. So we need to know how to protect yourself, to take precautions. All right, back to COVID-19. So this is from Mayo Clinic, and they're saying, well, who's at higher risk? We're going to refer to this little list a couple of times going forward. Who's at higher risk of serious symptoms? Well, older age, kind of talked about that. I got dinged twice. I'm in the older age category now. I should be afraid, shouldn't I? Number 2 is diabetes and obesity, heart disease, weakened immune system, chronic kidney or liver disease. And I'm going to show you factors that connects all of those together. And so really it's only one thing you need to do to support yourself. Well, isn't that a gift, huh? Type 1 or type 2 diabetes can increase your risk of serious COVID-19 symptoms. I kind of assume you probably knew that. Having a higher body mass index is considered overweight, obese, severely obese, or increases this risk. Diabetes and obesity both reduce how well a person's immune system works. Diabetes increases the risk of infections in general. I find this unuseful information, not very useful information. It's just sort of saying, what, heavy people get sick? It doesn't help me at all, because that's also equally not true for other categories. We're going to get deeper into this. So this risk can be reduced by keeping your blood sugar levels controlled and continue your diabetes medication and insulin. What if you are overweight or obese? Aim to lose the weight by eating a healthy diet and getting plenty of physical exercise. I find that so general as to be useless. But that's what the Mayo Clinic put out. Why is this true? It's of course true, but it's not specific enough. The answer will surprise you. From past videos, I went deep into flu, glutathione, vitamin D, and it's not all the same thing. Each time the topic has evolved. But now we're going to evolve that topic even more, and I do believe this is rather surprising. I'm going to simplify some of these things. Basically, new research, now that I've gotten into a lot of my data and learned to do scatter plots and spreadsheets and so on, I've got to test some of the theories out there. But anyways, if you really want to get into this topic, these are past videos. I'm going to give you some punchlines for each one. Why people die from glutathione deficiency. What you haven't been told about vitamin D changes anything. The punchline there is, if you have a liver problem, which were actually all those 5 conditions had a liver problem as a primary issue, diabetes, of course, and insulin resistance, of course, that means they are not being able to produce the glutathione that's required to activate vitamin D. So your vitamin D doesn't matter how much you take if you don't have enough glutathione to activate it. We'll get into that. Number 1 discovery that will allow you to completely eliminate the flu season. That one thing we learned from COVID that will save your life. A lot of information came from COVID. But now I'll show you what the labs show. I didn't do that before. I went from research before. Now I'm going to show you what our labs show to support these conclusions from actual people. And it's not what I expected. Okay, again, another list, how to survive the flu season. Feel free, it's a playlist. Go on, link and watch that. It's very valuable. I'm going to repeat only a little bit of that. I don't feel I have to go into repeating it all before, but it's very important, especially for those categories I named. So there's a secret as to why diabetes and obesity have the highest risk for the worst outcomes from respiratory viruses. But first this. a warning. What not to do when you have the flu, RSV, COVID, etc. Do not take aspirin. Do not take aspirin. Aspirin's 4,000-year history. It's 2000 BC and you have a headache. What are you going to do? Well, you're not going to take aspirin. You're going to take, I'm going to give you a little history back here. Yes, it did go back 2,000, arguably 4,000 years in Chinese herbal medicine and into Ayurvedic medicine. But, and you can say in native, North American native botanical medicine, indigenous medicine, they used willow bark. They didn't take aspirin, which is a concentration. So aspirin really came out of August 10th, 1897. A German chemist named Felix Hoffmann created a chemically pure and stable form of salicylic acid, which is aspirin. The drug, which came to be produced by Bayer, the company he worked for, it introduced a new world of pain relief and one that relied on an old age cure. So they concentrated it and they synthesized it. So it wasn't an herb, which has a lot of different things working in a larger context. 4,000 years ago, the Sumerians, you know where the Sumerians are from? Think of Cyprus, think of certainly the Middle East. Both Chinese and Greek civilizations employed willow bark for the medical use more than 2,000 years ago, and the Chinese also used poplar bark and willow shoots to treat rheumatic fever, colds, hemorrhages, and goiter. So having studied Chinese herbal medicine 4 years and acupuncture for 3, as well as naturopathic medicine for 5, do you think I have a student loan to prove that? I do. Is that there is no such thing as in Chinese herbal medicine as here, just take this herb. It's a formula, and it's a formula that's built on that particular person's tongue and pulse and basically exam. So not everybody gets the same formula. They get a formula for that person. Isn't that insightful? Each person's different in their formula, and that formula evolves. They don't stay on this one for like 3 weeks. And the end of a couple of days, as her condition changes, the formula changes. So there's no such thing as they all had a headache and took willow bark. They did not. It was in a formula for that person. Why should you not take aspirin? Take 2 aspirin and call me in the morning. Remember that one? Don't do it. Aspirin is a killer. A lot of information is coming out and has been coming out, and I'm just going to give you the headlines, and you can go look at this yourself. But the secret history killer of the flu of 2018, the history was this. And there's links and the names. It's like 1918, the flu epidemic was probably the deadliest plague in human history, killing more than 50 million people worldwide. Now it appears that a small number of deaths may have been caused not by the virus, but by a drug used to treat it, aspirin. So that came out in 2009, and it goes through all that, really interesting. So it just says that high doses of aspirin, amounts considered were unsafe today, were commonly used to treat the illness then. So it had just come out, so we can say, all right, they didn't know how to use it. It just came out. It wasn't like dosed out. They certainly didn't know the mechanisms of action. It was just like, hey, this is great. If your son or daughter or you're having a tough time, take it. You'll feel better. And it made a lot of problems. So the hypothesis is this. Aspirin contributed to the incidence and severity of viral pathology, bacterial infection, and death, because physicians of the day were unaware that the regimes, the amount they were giving, produced levels associated with hyperventilation, pulmonary edema, your lungs filling up with water, which is what you feel when you have the flu, right? I can't breathe. My lungs are just so full of mucus, right? Pulmonary edema in 33% and 3% of recipients, respectively, hyperventilation and pulmonary edema. Today, pulmonary edema was found at autopsy in 46% of 26 salicylate intoxicated adults. So now they're going, wait a minute, I think we're seeing a pattern here. In 1918, the U.S. Surgeon General, the U.S. Navy, and the Journal of the American Medical Association recommended the use of aspirin just before the October death spike. And it goes from there. Interesting. So the point is, aspirin specifically and NSAIDs, non-steroidal, anti-inflammatory medicines in general, may increase pulmonary edema. Exactly what you don't want during a respiratory virus. So if it's contributing to your lungs filling up and suffocation. Remember in COVID, we talked about all those people on ventilators, right? Ventilators is a big thing. Ventilators are running out of ventilators. Why were they ventilating? It's because their lungs were filling up with mucus. They were getting pulmonary edema. Aspirin misuse may have made the 1918 flu pandemic even worse. From the 1950s to the 1980s, thousands of deaths among children following influenza and other infections were unexplained until studies identified aspirin as the major contributor. So Reye syndrome, toxicity, which is vomiting, hyperventilation, delirium, and coma with brain swelling and fat in the abdomen and the liver, and proximal tubules, kidney, liver and kidney, remember those are the 5 reasons, developed after approximately 4 days of salicylate therapy, with reported mean daily doses of 25 milligrams per kilogram body weight. Adults with salicylate toxicity present mainly with abnormal consciousness, delirium, and respiratory distress. Recently, influenza deaths have been attributed to salicylate activities. It's only in the last few decades that researchers have connected aspirin use to the increase in influenza mortality. Oh my gosh, salicylates are a weak acid that crosses the cell membrane relatively easily. Thus, they are more toxic when blood pH is low, i.e. high anion gap. And by the way, I did a whole video, a couple of videos ago on anion gap, and the link is right above here if you want to get into what is anion gap. So you basically can make slightly more acidic blood. That's what they measure, anion gap. That's how we know it's getting more acidic. And for diabetics, they're more predisposed to that as their blood gets more acidic, they get slowly and dangerously close to a thing called diabetic ketoacidosis, which is not the same as nutritional ketosis. Okay? So excretion of salicylate increases when urine pH increases. So an increased pH is alkaline. So a low anion gap. So you want to be in a low anion gap. So drugs that increase urinary bicarb should be avoided because they worsen metabolic acidosis, and that's what we talked a lot about in that video, and decreases blood pH. The most common salicylate is aspirin. You know that. Aspirin misuse may have made 1918 flu pandemic worse. That's a big deal. So aspirin misuse may have made the pandemic worse. So here is a list of what we're talking about, anion gap. Here's acidic. So these are non-emergency levels. So these are people that I got. These are the data that people who come to see me. I'm not an ER doc. So these are supposedly healthy. They went in and had their blood test. But these levels, let me read this to you. So it is only in the last few decades. Here we go. Excretion of salicylates are worse when the urine pH increases, becomes more alkaline, metabolic acidosis, and decreases blood pH. The most common salicylate is aspirin, as well as Pepto-Bismol, if you will, bismuth subsalicylate, it's Pepto-Bismol. So those are the 2 things that contribute to this. And so this is an anion gap. And by the way, I have these 2 columns. One's in green. Those are people that are not insulin resistant, and those are in red. So you'll find that those who are insulin resistant are the ones that have higher levels of what they call the anion gap. So these are people whose insulin resistance is over 1.4. We're going to delve into that. The use of aspirin salicylates is known to increase the risk of Reye syndrome if used during a viral illness. Do not do it. The underlying problem with the use of aspirin during a viral illness is an inhibition of fatty acid metabolism, what they call OXPHOS, oxidative phosphorylation. Not going to go into it, but basically it makes your brain swell. Not only do you get pulmonary edema, but you get encephalopathy, so you're getting swelling. So the end result is encephalopathy, swelling of the brain. That recently came out in 2018. So that is a big deal. So it's not a free lunch. It's not like, hey, I'll take the most benign thing in the medicine cabinet or the kitchen cupboard or wherever you keep these things. Do not do it. Okay, so what to do and why to do it. What the actual data shows and what is relevance to you. Let's take a look. Okay, so here's how I'm going to here's where my data comes from, right? The people I see, my clients that take their labs, that's what labs look like. Mostly it's LabCorp now. Put it on a massive spreadsheet, and from them, I do comparisons, and that's where I get my scatter plots, okay? Raw data, people, their labs, raw data, 2 spreadsheet, 2 scatter plots, and that's what we're going to look at. So we're going to be looking at scatter plots. We're not going spreadsheets. But why is this important? It shows the actual relationship between labs for a better understanding. Really, it does, even for me. So what if every lab result was divided into 2 groups of people? So all those people, right, all those labs, that I took all those labs and they are going to be insulin resistant category, HOMA-IR over 1, or not insulin resistant people, HOMA-IR under 1.4, right? So that's what we're going to look at. You're either in the green, non-insulin resistant group, labs, or you're in the red, insulin resistant group. That's what we're going to do, and we're going to get a profound insight looking forward into that way. Okay, so to review, what is insulin resistance? Briefly, I'm just going to give it to you, right? We broke down the labs into insulin resistance and non-insulin resistance. And so what does that mean? How is insulin resistance measured? HOMA-IR, insulin resistance. So it's the homeostatic model assessment of insulin resistance. It's the standard used for assessing insulin resistance. So insulin resistance is an empirical, is an actual number that we're going to use. We're not like, oh, I'm feeling a little insulin resistance today. What do you think? No, we're not doing by the how you feel. We're doing it by the numbers, okay? So these are the two formulas, depending if you're in the metric system, if you're not in the metric system. So you can figure it out either way. I tend not to use those formulas. I mean, I do use the formulas, but I go online, and I'm going to show you in a second. So drill it into your brain. Insulin resistance is anybody who has a HOMA-IR number over 1.4 in North America, well, 1.4 period, depending on what formula you use, whether you're metric or not, but it's 1.4, okay? It's considered insulin resistant. All right, got that out of the way. Here's where I go. Here's the link for that. I simply plug in, whether it's a client or a patient or my own, fasting insulin, fasting glucose. You can toggle the system here to metric or non-metric, so it's a one-stop shop. It's great. And it gives you a number. Boom. I mean, it's pretty easy math. You can do it either way, and you can double check it and make sure it all works out. But that's what I'm talking about. That's what we're using. How to find out if you're insulin resistant. You need two labs, and I'm painting it for you. Fasting insulin, fasting glucose. The price of the labs are from LabCorp. It's $10 for insulin and $4 for glucose. Quest, it's a little more expensive. Add in a phlebotomy fee, and that's what you got. And if you have nowhere to go here. This is our link. We do not get a penny out of this. This is free, but this is where you couldn't do this 10 years ago. My whole gig here is to encourage you to take action on yourself, to understand your health so you can be responsible for your life. That it's in your hands. So don't go, my doctor told me to do this thing. You need to know why your doctor told you to do that thing. You need to know why you're on that medication. You need to know your labs. Not everything, but you need to know some basic labs. This is why I'm shoveling it in to saying it's important for you to know this. And stop saying, I don't understand. Understand. Do this. A closer look at glutathione. Some bad news coming up. If you're in my category of being older, what we know to be mostly true. Remember, the glutathione gap, covered this on a number of past videos. What is the glutathione gap? That's the difference between what you need. So it is the ultimate antioxidant in the body, and it does a lot of different functions, but we're just going to call it an antioxidant. It puts out all the inflammatory fires throughout your body, and you need to have enough of it. You need to have fire extinguishers throughout your house, right? Think of it that way. So, but the problem is, as we get older, we have fewer fire extinguishers. And not only do we have fewer of them, they get smaller. So we're getting cheated as we get older. That's one of the definitions of aging, I guess. But you can take some action that will change a good portion of that. So the anion gap is the difference of what you need, your level of inflammation, and how much of a fire extinguisher you need, right? So if you have a little fire extinguisher and you have a big inflammation, big fire, that's a big gap, okay? And that's what I'm showing. So as you get older, this gap becomes pretty apparent. Here's age down here. It's a good illustration of what the difference is. Here's something that I presented a number of videos ago, and I've only been able to verify half of this. I want to verify the whole thing and say, hey, this is absolutely the reality. But anyway, here's what it goes. Homocysteine increases during aging and glutathione decreases during aging. So on my spreadsheet, which is around 60 to 80 people at this point, I've only been able to 100% verify the glutathione decreases. I have not been able to verify in my data, and I'll show you that in a second, that homocysteine increases. Homocysteine becomes a toxin after this number right here, 11.4. So it's saying basically any male after 65 and any female after 75 has a toxic level of homocysteine. And I'll show you there, but that's not true with all the people that I've worked with so far. So I think that's a really population specific, but you go, well, look at the N size. They have 8,500 people, and you, Dr. Goldkamp, only just said you had 60 to 80. I'm going to believe them. That's what I would think too. I would believe them too, but I don't even have anything near that. I'll show you in just a second. So I'm going to show you my data relative to these two things that I showed you and that I've used in past videos. From what you just saw here, I sort of put it in a slightly different format. I'll say 65-year-old man should have, 11.4, and a 75-year-old woman on the average, given that data, was 11.4. So that's at the upper limit. That is the number of the upper limit. Beyond that is toxic, okay? And for their glutathiones, it's near zero. So we got that out of the way. So now what does actual data look like? Here's what I did. Let's look over to the right side first. We have glutathione. There's the range, so 176 to 223. So pretty straightforward. Glutathione goes down with age. It's a truism. It also exists. It's pretty easy to spot. Boom, that's it. Then I broke my population down into, right, the green side or the red side. They're either non-insulin resistant or insulin resistant. So what does that look like? Well, they both end up at the same spot. I would say that's probably because I don't have enough 80-year-olds that are both in both camps, you know. But what it shows is that non-insulin resistant people were always higher in glutathione, reduced glutathione to be more specific. And that decreases with life, but it's always higher than the insulin resistant people. Okay, pretty interesting. Now go over to the left side, glutathione versus HOMA-IR. So all of these are all my data, right? So what does all my data show? Again, it says, well, glutathione goes down with HOMA-IR. So the more insulin resistant you get, they get, regardless of gender and regardless of age, the more insulin resistant they get, their glutathione gets lower and lower and lower. All right, let's break it down into non-insulin resistance. Remember, non-insulin resistant is under 1.4, so it's just a smidgen, it's just a splinter of that whole range. So here you go. Yes, that also goes down within the narrow range, and I'm going to show you a little more in a second. And now we look at the insulin resistant people, and you say, yeah, it goes down there too. So there's a slight difference. One, it seems to be here for it still goes down as an individual, as a non-insulin resistant person moves and goes from even within 0 to 1.4, as it goes down, as you get worse or more towards insulin resistance, your glutathione drops. So even in the non-insulin resistant group, that happens. And of course, it happens in the insulin resistant group. So the reality from my data is a little bit different. Yes, glutathione decreases with age, and yes, glutathione decreases with insulin resistance, HOMA-IR. But homocysteine decreases with age. Over here, this is not as predicted. So what I did is the same thing. I even broke out those two populations of insulin resistance and non-insulin resistance, superimposed them right on top of each other, and it's pretty much the exact same line, and it's most definitively going down. It is not going up. So for, I don't know if I have 60 to 80 in there someplace in the spreadsheet and all that, but it's enough people to say it's more than just a couple people. So it's so diametrically different to that study, I question it. No, I don't have 8,500 individuals. I only have 60 to 80. Now let's go over to the left side, homocysteine versus insulin resistance, right? So we have everybody. It shows, hey, the homocysteine actually goes up relative to insulin resistance. Homocysteine increases relative to the degree of insulin resistance. Homocysteine also increases with the non-insulin resistance, but the inflection point is really at 0.6, which is really interesting. So at some point, we know with insulin resistance, your homocysteine starts to increase. I didn't know it was that low. It starts at 0.6 relative to my data. So homocysteine increases with insulin resistance. So maybe that 8,500 group study was dealing with people who were severely insulin resistant. I don't know. And obviously it's worse for insulin resistant people. Okay, well that was interesting. Okay, I wanted to go back to this particular slide with a little more detail. So this is glutathione with age. We know it decreases with age. This is everybody. It's not differentiated between insulin resistance and non-insulin resistant and insulin resistant people, but it's useful anyway. But this isn't the bigger picture. Glutathione decreasing with age is not the bigger picture. It's a big contribution, and if you didn't know that, now you do, and sorry to disappoint you, but there's something you can do about it that you need to know about. Yes, it decreases with age, but it decreases much faster if you are insulin resistant. So knowing your HOMA-IR number is very important. It's important relative to your vitamin D. It's important relative to general health. Look at the difference between non-insulin resistance and insulin resistant people. Here's glutathione, and I mentioned that briefly. Still, you know that non-insulin resistant people always have a higher level of glutathione than insulin resistant people over age. Now let's compare glutathione relative to inflammation. So inflammation is CRP, C-reactive protein. It's the standard used. You want under 1. So under 1 is considered a good number, right? 9 is you should be at the ED or the ER. That is starting to get pretty high. So, but these are people that came in as clients and they didn't say, hey, I'm high inflammation. They didn't even know their inflammation. So you come back and you go, what the heck? Do you tell me more about your story? But it's important to know the two groups. Red is always going to be insulin resistant group, right? And green is always going to be the non-insulin resistant group. So what are we seeing here? This is profound. So as inflammation gets higher and higher and higher, what do we see? The insulin resistant group, they can't increase their glutathione because glutathione is something you generate. You don't eat glutathione, even though it is in plants and so on and so forth, but you don't eat it, you make it. So your glutathione is direct ability of you to be able to make it, right? So you take that lab, it's like you being able to make it. Unlike you look at red blood cells or hemoglobin, you have to eat iron. You have to eat meat preferably. And that's what you're measuring. So a bad diet will show definitely in the iron category and red blood cells. A bad diet, you could say, well, obviously will contribute to glutathione, but it's more about insulin resistance and more about your genomic sort of status. So here we go. Insulin resistant people, their ability quickly drops very quickly. Whereas non-insulin resistant people, because they are stimulated, the inflammation's there, they upregulate, they upramp, they increase their production of glutathione because they have a healthy metabolism that allows them to do that. The factory, as I often call it, your glutathione factory, methylation, is working well. And it goes, all right, the demand is up. We need to increase our glutathione. Whereas those who are insulin resistant have a poorly performing factory and they can't meet the demand and they start to get into trouble. So these people cannot increase their glutathione, whereas non-insulin resistant people can, and they do increase it. So what you need to know is that there are two groups of people that have low glutathione, which is what we've been talking about. This group can change, and this group is insulin resistant people. One is they can change their diet, they can change some of their parameters, and they can measure their, their whole status with a glucometer and a continual glucose meter, CGM. All those things are helpful, and you can learn to move out of insulin resistance and diabetes, all of that. You can drop weight. Those are pretty straightforward things you can do. And this other group, though, is about genomic mutations. I'm going to talk to this in a second, and I've done a lot of videos on this before. And what you're going to find is their genes are limited, and always often, and I'm one of those people. And so you are continuously kind of glutathione deprived. You have a difficulty. Even if you're a non-insulin resistant person, because you have some of these mutations, you will still be compromised. And so you need to take care of that. And there's a way to do that. Okay, so you have two groups that come into low glutathione, insulin resistance and those who have the mutations, the SNPs, right? They have a decreased ability to generate reduced GSH is reduced glutathione. So the point here is that you can have a combination of insulin resistance, HOMA-IR, versus any, and this is just a picture I brought up of some of the genes that I test for. This is the common one, and we're going to get into a little more depth later on. This is MTHFR, methyl tetrahydrofolate reductase. It's a mutation. There's other mutations of this enzyme as well. These are people, if you have some of these, you are at a compromised level. That is, your ability to methylate, to turn genes on and off, is impaired. The interesting thing is, the reason it is impaired is you evolve that way. It's not necessarily a bad thing. We all our ancestors come 50, 100, 200,000 years ago, as we became humans, had to co-evolve with malaria. And one of the strategies was to make yourself as inhospitable to malaria as possible. So what that meant, so malaria is a red blood cell parasite. So you had to make your red blood cells very vulnerable and to, in essence, die off. So if you got the mosquito, the Anopheles mosquito, and you got your malaria, the malaria goes, this person's body is terrible. I'm not going to stay here. And variations of that strategy, where any of these mutations, certainly the methylation that compromised your ability to methylate, but also sickle cell anemia, they were survivors in their environment to survive malaria. G6PD deficiency, and I've talked about these in past videos, was an evolved strategy from generation after generation to outlive malaria, right? To have another generation of offspring to outlive malaria. So pretty interesting. So we all came from that world, whether it's of Africa or wherever you think that you came from, right? We're all part of that. And we have it to degrees. Some still have remnants of it, like myself and my wife as well. So can you imagine having both of this? You'd have an impairment here and your insulin resistance. You're really much more vulnerable. That's the point of all this. Okay, so how does COVID-19 fit into all this? SARS-CoV-2 virus interferes by, and this was from a past presentation, it says reducing SAM or SAMe levels, which is S-adenylmethionine level, using up methyl groups for viral replication. So by simultaneously increasing demand, so it is, what is it? So let's say your methylation is a factory that makes glutathione, and it makes SAMe, and it makes other things that are important for you, neurotransmitters as well. So it's an important factory. Now you get this respiratory virus, SARS-CoV-2, COVID-19, flu, RSV. it says, I got to borrow that apparatus. I got to borrow that factory a little bit because I'm going to use the same mechanism that you use to make it so we can virally replicate and infect you. So it not only stops your ability to, or reduces your ability severely to make glutathione another thing, but it also is used to make your virus worse. So simultaneously increasing demand, which is increasing the virus, and depleting the supply by stealing the apparatus, the methyl groups. So COVID-19 wreaks havoc with the body's methylation metabolism pathways, ultimately leading to an imbalance of folate, B12, homocysteine. Altered amounts of these nutrients influence how a person reacts to an infection. That's not me saying it. This was 2017, an Italian study called The Human Genetic Determinants of Viral Diseases. Fascinating, completely fascinating. So here's a little bit of the diagram there, and I put them together into what I call the COVID Studies Yearbook, because there was so much good information that came out of COVID in 2021. MTHFR, that gene that I just pointed out, and COVID studies. What does it show? So the MTHFR, this is just general, your methionine cycle and folate cycle. Together they're called the methylation cycle, if you will. And here's SAMI and all these things are, but I'm not going to get into the detail. So if you have a problem with this gene right here, you're going to have a problem with making SAMI. You're going to certainly have a problem with making glutathione. So this is the ultimate glutathione factory. This is the final car, if you want to think of a car factory. It's not working. And so the idea was your glutathione decreases for life and that your homocysteine increases as you get older. It has a lot of logic to it. I just didn't see it in my data. This gets toxic, and something that you need to prevent inflammation from taking over for a lot of reasons. Glutathione you can't make for yourself. And this is from another study in 2021 called a methyl group assault. And it was defining COVID as a methyl group assault. And so all the other countries and all the other information that came out about how they were dealing with their outcomes, they were finding glutathione, NAC, and a few other things that supported their methylation cycle were actually much better than any of the medications that were being suggested at the time. Okay, deeper study. These are some of the SNPs that affect your ability to make glutathione. So I believe this is mine, actually. And here we go. So it basically says I'm homozygous for this. Oops. I have a few other heterozygous, another homozygous. So I have my problems. I have my problems with making choline as well. It would be worse if I was a woman because it's driven by estrogen. Collectively, I got my problem. So therefore, I am at risk. I'm not insulin resistant, thank goodness. All right, so here again is what I consider the three genomic bottlenecks, the big bottlenecks first. MTHFR, MTRR, you really don't need to know these names. CBS, cystathione beta synthase, is the thing that converts homocysteine down to glutathione. There's a number of steps, so it's not just one, but there's a number of mutations that can go wrong that I pointed out on that list. And so that's where in life it says, as we get older, homocysteine increases, and at the same time, our glutathione decreases. There's the dam analogy, remember that? But it doesn't have to. So I'm leading up to it doesn't have to. Okay, another yearbook reference, the correlation between MTHFR C677T, allele frequency, and the coronavirus mortality. Not like they did worse. They did do worse. They did worse to the point they died. It was found to be 85%. Geez, the correlation between homocysteine level and COVID-19 severity of infection has demonstrated that homocysteine, that's the shorthand for homocysteine, over 16 micromoles per liter. Now I go, whoop, I just threw in the client's labs of that homocysteine. Here's homocysteine, goes down here, and then it goes back up there. You can see these were non-hospitalized people that came to see me, and they didn't know how bad they were. These levels predisposed them to a very bad COVID outcome. They got here genetically, either by, more than likely, I can't remember these particular people, so I had to go back and check it all out. I could figure it out. They're already predisposed to a bad outcome. They're already high risk. This didn't even say anything about insulin resistance or not. So homozygous carriers of this variant shows higher homocysteine levels than normal subjects. COVID-19 spreading across the world correlates with C677T allele of MTHFR, the gene, prevalence in 2021 Italian study. So just what, 2-3 years ago. Amazing. All right, now add inflammation that results from any of the respiratory viruses, just inflammatory process in general, what happens? So I did CRP, you know that's inflammation, relative to glucose. So inflammation drives up glucose. Think of stress. So if I scared you and stressed you, if you were stressed for whatever reason, I could go, your glucose is pretty high right now. So it's automatic. So, and look what happens. Here's glucose. Glucose goes up a lot with stress, certainly while you're fighting an infection. And here you go, what's this big loop here? Well, when we figure if these were insulin resistant people and they're getting inflammation here, and they already have this corner here, their glucose is zoomingly high, they're on medication. So there's a point that I put this line here saying the unmedicated projection would have been way up here, which is death right over here. So they had to be medicated to bring these factors down. So it's an area of serious damage. Very high inflammation, very high blood glucose, but not for everyone. Watch this. We react differently when we get a respiratory virus. We as people react differently. Here again, here's the insulin resistance people, right? Their glucose versus say the same chart. They go, wow, look at that, really increased. So insulin resistant people goes zoomingly high glucose increases. And you go, why does it come down? That's the medication kicking in at this point because it's very dangerous here. Whereas we look at the non-insulin resistant people with the same level of inflammation, what do we find is that their glucose actually dips. It actually goes down a little bit. Maybe it rises. But in the course of 1 to 9, it really hasn't changed that much at all. And when you know the range for glucose is 65 to 99 as an acceptable range, should be lower, but that's the acceptable range. In terms of all that inflammation, non-insulin resistant people did not even get out of range. Oh my gosh. So when you are sick, CRP obviously increases, but there's a difference. So when insulin-resistant people get sick, they really get sick. Next, vitamin D correlates positively with glutathione levels and negatively with insulin-resistant levels. Type 2 diabetic patients, 2014, vitamin D status in hospitalized people. So these are people coming in doing so poorly that had their blood tested. Thank goodness there was vitamin D there. So now let's look at that a little more closely. This is insulin resistance, HOMA-IR, vitamin D. So we find the worst HOMA-IR, the lower vitamin D. Makes perfect sense, right? I told you about the liver is compromised. Over here, here's the data. We're not going to go, I'm just showing you where I got this data. It was actual real data of non-insulin resistance people. Here's the HOMA-IR number up to 0.5 is 1.4. And insulin resistant people, continuing from there, 1.5 to 25 and others. So we see it fell a lot. So the client's labs, the point is being non-insulin resistance is far more important than your level of vitamin D, but you must pay attention to both, really. Don't even wish it was that simple. Vitamin D correlates negatively with insulin resistance. This is my data. It says, absolutely, that's the case. All right, but the opposite is true with homocysteine. Homocysteine in vitamin D. Vitamin D in the bottom, homocysteine here. It says, wait a minute, as vitamin D goes down, homocysteine decreased. You go, well, isn't that a good thing? I guess I can't explain that. I'm just showing you the data that there is an inconsistency with homocysteine relative to vitamin D. How could this be true? That inconsistency. Let's look at the big picture. Maybe there's another explanation. Okay, vitamin D. Remember I told you, how could glutathione limit vitamin D? Vitamin D, whether you get it from the sun, whether you get it from eating fish, whether you get it from supplements, goes to vitamin D to the liver activates it to send it to the kidney, and then the kidney activates it to support your immune system and bones and muscle and all the other fun things that vitamin D does. But if your liver is preoccupied by being insulin resistant by a lot, it's not really going to pay attention to, oh yeah, it has this other job to do, which is to activate vitamin D and to save your life. We're not going to do that today. Or we're going to do it very poorly. So this connection is the liver. So if you don't get by here, if you have a compromised stat state, we got other issues. All right, the point is just breaking it down, liver to kidney. It adds a hydroxyl group. Do you really care about that? Probably not, but the liver has to act on vitamin D so that the kidneys can turn it into a hormone and save your life. The degree of liver dysfunction, this is important, the degree of liver dysfunction is directly related to its ability to create glutathione. So there's a conclusion, directly related to the ability to create glutathione. The stages of liver disease, normal versus cirrhotic. We just think of cirrhotic as, well, there's an alcoholic, it's cirrhosis. Well, it happens in degrees of what they call fatty liver, and you can have alcoholic fatty liver disease, and then you can have non-alcoholic fatty liver disease, which is actually getting very, very popular in the last 30 years. However you got there, your liver is pooping out and it's not doing that one thing, one of the most important thing, which is to create glutathione. All right, so non-healthy people, non-insulin resistant people are down here. Insulin resistant people are up here. So the percent of glutathione deficiency. But an example, investigating the causes of decreased, this is actual report 2015 from the US. It says investigating the causes of decreased levels of glutathione in individuals with type 2 diabetes. You go, why would they do that? Probably because I just told you why, right? It's like, wait a minute. So what they find is tuberculosis, TB, remains an imminent global burden. This is their words, not mine. With 1/3 of the world's population gets TB, is infected with Mycobacterium tuberculosis, otherwise known as TB. Individuals with compromised immune systems are especially vulnerable to TB. Makes sense, right? But here's the puncher, here's the kicker. Individuals with type 2 diabetes are 2 to 3 times more susceptible to TB than those without. Therefore, it's that inability to produce glutathione. They can't say it's causative, but it is a big anti-inflammatory, antioxidant that they can't even make. And so therefore they're wide open to being decimated by a number of things, but certainly in this case, TB. Individuals with type 2 diabetes have lower levels of glutathione, reduced glutathione, due to compromised levels of its ability to synthesize, to make, to create, to upregulate glutathione and metabolism enzymes. 2015. If your liver is compromised, it can't convert vitamin D effectively. It doesn't have enough reduced glutathione. Its ability to activate vitamin D is decreased, limited, compromised. It can't save your life. When you can make your own glutathione, it makes a big difference. This is the whole big breakdown. So why would you be concerned about insulin resistance versus non-insulin resistance? And to me, this is the lens in which you should look through all labs. Every doctor should look through all labs. And so what I did is I chose 2 liver enzymes here to further my case. So furthering my case is GGT, gamma glutamyl transferase. Why would you care to know about this? This is what they look at people when they go, this person's in a really bad compromised liver. Usually it's about alcoholism. So it says when the liver is damaged, GGT may leak into the bloodstream. So this is when it shows up in the blood. It says you have high GGT, you got a liver problem. It's definitively liver. Okay, also I looked at ALT, which is the most closely, those who have high ALT, it's a sign of fatty liver. So it's one of those things they track. So most closely related to fat accumulation in the liver, used as a surrogate marker for non-alcoholic fatty liver disease. So if you can make your own glutathione, it lower liver enzymes. Holy smoke, let's look at this. So this is one of the things I test for. Here we go. Here's everybody. Here's everybody together, all non-differentiated data. And you see that glutathione is here. So as your GGT goes lower, gets healthier, you get more glutathione. So that's everybody. I put in non-insulin resistant people, and what do we see? It shows that as their GGT rises, their glutathione increases. They have the ability to make more. It's not like a finite little stash of gold in which you have to give it away. They have a healthy metabolism. They can make more glutathione. So they start low, but they end up more glutathione. Isn't that amazing? All right, ALT, same thing. I put down the ranges if you want to look at all that. ALT, which is the same thing. Here's everybody together. ALT, if your ALT is high, you have low glutathione. When your ALT is low, meaning you're healthy, you have more glutathione. But the non-insulin resistant people, as their ALT rises, their glutathione increases. Mind-blowing, eh? So when you start looking at the world between these two things, you realize that insulin resistance is really about a liver compromise. It compromises a lot of functions, but right now I'm talking about glutathione because glutathione is going to be something we can do something about. CRP, enter inflammation. Now we have CRP up here and glutathione down here. We have everybody together as their CRP increases, right? So as this number gets higher, their glutathione decreases. Now that's for everybody. So now for the non-insulin resistant people, we find that as their inflammation rises, right? Their inflammation rises, their number gets higher, so does their glutathione. Holy smokes, that's a big deal. What happens when your immune system begins to fight a respiratory virus, the flu, RSV, or COVID? This is what we're talking about. So back to COVID-19, who's at the higher risk of symptoms? These conditions all have one thing in common, especially diabetes and obesity, but really we're talking about the same thing, and that is a seriously impaired ability to make glutathione. But remember, those with problematic SNPs, single nuclear polymorphisms, are also impaired, as you discussed. So now you know the secret. Having the appropriate supplements on hand will make a world of difference when you come down with any of these 3 respiratory viruses. So here's what you need for your viral respiratory first aid kit that you should have at home. What you need to have on hand and why. Coming up. So if this is something that you're interested in, that is a topic that I obviously go deeper in terms of labs, in terms of how to do it, in terms of why you would want to do it, various topics that you've seen that I've done in the past, then please let me know below in a comment. Till then.